All right, so we are going to start talking about equilibrium, which is chapter 15 in your textbook. And we've already talked about equilibrium a little bit. We mentioned it when we were talking about a saturated solution and how in that saturated solution you had ions that would be dissolved in the solution, and then you also had some solid that was at the bottom. And so that solid was dissolving, and then the ions were precipitating back out and reforming solid on the bottom. So you've been kind of introduced to that idea, but now we're going to talk about equilibrium from the point of view of chemical reactions. So I want to start with a definition. So equilibrium occurs when I'm going to change color here because this is really important. When the rates of two opposing processes are equal. So equilibrium is when the rates of two opposing processes are equal. So in the case of our salt solution, when the rate of the salt dissolving is equal to the rate of the salt precipitating back out, then we're in a state of dynamic equilibrium. Okay, so anyway, the way we want to look at this in terms of thinking about reactions is we have reactants and we have products. And you've seen arrows, one-way arrows, and then we've also shown you arrows which are pointing in both directions. And so when you think about some kind of standardized test like the AP exam, when they give you a reaction and you see a one-way arrow, that's going to be representing stoichiometry, some kind of process where if the reactants react completely with each other, you get all products or 100% products. If you have a limiting reactant, then you'll have some excess reactant left over. But if all of the reactants completely consume each other and you end up with all products, that's stoichiometry. And then in comparison to that, equilibrium is when reactants form some products, which then would also mean that you have some reactants remaining. And so that's a state of equilibrium. And the amount of reactants and products you have left, we're going to talk about that a little bit later. But for right now, think about stoichiometry as being all and equilibrium as being some. I'm going to write a reaction here because we had talked about the difference between strong acids and strong bases. So that would be something that you'd be familiar with. So if I have a strong acid, like let's say hydrochloric acid, and we had talked about when you put hydrochloric acid in water, it completely dissociates. So what that means is you get all ions. So in reality, what you really have is just your ions, and you don't have any of the molecular HCl left. So that would be stoichiometry. Compare that to something like acetic acid, which we know is a weak acid. And so when you have acetic acid, a solution of acetic acid, you have some protons, you have some acetate ions, and then you have much more of your actual acetic acid molecule that remains. And so that's how the two differ from each other. Okay, so now what I want to do is I want to look at a reaction where I've got A and B as reactants and C and D as products. And I want to talk about some language that we use when you're talking about the reaction going in the direction that we normally think of. So from left to right. So we're talking about this reaction. We call that the forward reaction. And then when you're talking about the reaction going in the opposite direction, which would be right to left, or from C and D going to A and B, we call that the reverse reaction. Now, you don't take the equation and flip it around. You continue to use it just as it's written here. But if we're talking about going from left to right, that's forward. And if we're talking about going from right to left, that's reverse. So now what happens as a reaction proceeds? Okay, initially, you've got your reactants that you have combined together in this container. And we've talked a little bit about this when we did those initial change final tables. You'll have some certain amount, I don't know, let's just say we've got a mole of each just to make it easy. So we talked about having some initial amount of our reactants and having nothing of our product. So that's what I'm talking about here. When we start that reaction initially, just reactants, no products whatsoever. And initially, the reaction goes in the forward direction. So A and B start to get used up, and C and D start to appear or form. And that continues. Then as C and D build up, there's enough of those to react and go back and form more A and B. And then as more A and B form, A and B react to form more C and D. And this continues until at equilibrium, I'm sorry, I can't write with this pen yet. I will get better. You're going to have some amount of, whoops, sorry, A and B and some amount of C and D. They do not necessarily have to be equal to each other. We'll talk about that in a minute. But what is true is that the rate of the forward reaction is equal to the rate of the reverse reaction. And so when your rates are equal, you are in a state of equilibrium. Okay, so let's look at this. I didn't want to go back that far, just a second. Sorry, I didn't realize that was still recording. Okay, so what we want to do is we want to look at what's happening graphically. So we can look at this two different ways. We can look at concentration versus time, and we can also look at reaction rate versus time. And what I want to do is I'm going to change the molar ratio on this so that we have twice as much A as we do B. Okay, so initially we have a certain amount of A, and I'm going to make a light blue. So we have some concentration of A, and over time, that concentration of A is going to decrease. And then we also have some amount of B, which should be half of whatever this is if we're not going to run out of it. So that will be decreasing as well, but the slope is not going to be as extreme because it only has a coefficient of 1 instead of 2. C and D, I'm going to change their colors. Let's make C green. Let's make this easy and let's only have one product. So let's say this is a synthesis reaction. So initially we have no C, and C and B are in the same molar ratio, so their curves are going to look similar. They're just going to be flipped. So as time goes on, the amount of C starts to build up, starts to increase, and then eventually these are going to level off where our concentrations are not changing with time. Okay, I think my C curve looks a little bit more like my A curve, and I don't want it to because they don't have the same coefficient. So I'm going to go back and adjust that a little bit. This should look more like B. Okay, at this point where you can see that their concentrations are no longer changing with time, equilibrium has been established. Now, in terms of reaction rate, this graph is going to look a little bit different. Because if you remember from one of the earlier slides, let's go back to this first one, we talked about how equilibrium, the definition of equilibrium, is when the rates of two opposing processes are equal. So one of the things that we should notice with this graph is because we're looking at rate, when the rates of these are equal, we are at equilibrium. So A is a reactant. It's going to be decreasing over time. Let me change that and make it look more like it actually should. C is a product that's going to be increasing over time. And let's just look at A and C. So if you look at this right here, you notice that these rates are equal, or would be equal if I could draw a straight line, because really this green and this blue should be the same. So what that shows you is at this point we are in a state of equilibrium because the rate of the forward reaction, which is light blue, is equal to the rate of the reverse reaction, which is green. So graphically, that's how we represent it. Now, in terms of what we would actually see, macroscopically, what we would see with our eyes, we wouldn't see anything. It would really be kind of boring. Microscopically, which would be magic school bus level, you would see that you had initial amounts of reactants. And then you would see the concentration of the reactants would be decreasing. The concentration of the products would be increasing. As that happened, the rate of the forward reaction is starting to slow. The rate of the reverse reaction is starting to speed up. So as that happens, then that allows more A and B, more reactants to be produced, which then speeds the rate of the forward reaction. And that process continues until those two rates are equal. And then we are at a state of equilibrium. I want to Okay, so what we have macroscopically, we're not really seeing anything. It appears that the reaction has stopped, even though in reality, microscopically, it's still occurring because concentrations are changing with time, because we're forward reaction, reverse reaction, but the rates are now equal. So now what we want to do is talk about the equilibrium constant itself.